Welcome to this video, everybody. I am Esteban Contreras. I'm a postdoc from the Institute of Mathematics of UNAM under the advisor of Dr. Juan Jose Montellano Ballesteros. This time, I'm gonna tell you about certifying recognition algorithms from complete partitions. Throughout this video, we are going to talk about hereditary properties and minimal obstructions, also about certifying algorithms. We are going to define exact neighborhoods and complete partitions, and we are going to define also what a matrix partition is. With all these definitions and these tools, we are going to speak about the main topic of this video, which are certifying recognition algorithms from complete partitions. Well, let's start with hereditary properties and its minimal obstructions. Any class of graphs is going to be a property of graphs. For example, the class of all connected graphs is the property of being a connected graph, and the class of all Hamiltonian graphs is related with the property of being Hamiltonian. In this video, we are not interested in any property of graphs, but in some special properties which are the hereditary properties. A hereditary property of graphs is a property which is closed under vertex deletions. That means if you have a hereditary property and you have a graph with this property, anytime that you delete one vertex of this graph, the remaining graph is going to be or is going to have also the same property. Connected graphs and Hamiltonian graphs are not hereditary graph classes because if you have a connected graph with a cut vertex and you delete that vertex, then the remaining graph is not going to be connected anymore. The same way, if you have a cycle, which is a Hamiltonian graph, and you delete any vertex, you are going to obtain a path which is not more a Hamiltonian graph. But there are also some interesting properties of graphs which are hereditary. For example, the property of being a k-colorable graph, in particular the bipartite graphs, or the property of being a complete multipartite graph. For any hereditary property of graphs, we can define the minimal obstructions of that hereditary property as the graphs that doesn't have the given property, but such that for any vertex, if we delete that vertex, we obtain a graph with the hereditary property that we are studying. For example, for the case of bipartite graphs, we have the 5 cycle, which is not a bipartite graph for sure, but if we delete one vertex, any of them, we obtain a graph which is isomorphic to P4, which is in fact a bipartite graph. Also, for complete multipartite graphs, we have an example of a minimal obstruction, which is the disjoint union of K1 with K2. And why are we interested in these minimal obstructions? Well, this is because any hereditary property of graphs can be characterized by means of its minimal obstructions in this way. A graph G has a given hereditary property P if and only if G doesn't have as a minimal obstruction, if G doesn't have as an induced subgraph any of the minimal obstructions for the hereditary property P. Many results in graph theory has this form, and they are specific for a specific hereditary property of graphs. For example, it is well known that a graph G is bipartite if and only if it doesn't have induced subgraphs isomorphic to an odd cycle. Also, another well-known result is that a graph G is a complete multipartite graph if and only if it doesn't have the disjoint union of the complete graph with one vertex and the complete graph with two vertices as an induced subgraph. Okay, now let's change a little the topic, and now let's talk about certifying algorithms. Well, once that you implement any algorithm, there can happen three things. The first thing, which is the more desired case, is that you obtain, anytime that you run the algorithm, you obtain the correct output. Okay? Something which is undesirable is that at the time you run your algorithm, you obtain an output or something that you detect as a mistake in the algorithm, and this is undesirable for sure, but it is preferable than the third option, which is that the algorithm produces an incorrect output but you don't notice. So that incorrect output is hiding a mistake with the algorithm or with the implementation of the algorithm. And this is the worst case because you don't notice anything at all. Okay? So in order to avoid these problems, we have the certifying algorithms. So a certifying algorithm is simply an algorithm that together with the output, it returns also certificates that helps proving that the given output is correct. Okay? Such certificates must be verifiable efficiently. Okay? You must be able to check them more efficiently than running the algorithm again. Okay, for the special case of decision algorithms, these algorithms are the algorithms whose output is yes or no. These certificates are classified as yes certificates for the output yes and no certificates for those outputs no. Okay? Well, the minimal obstructions are important in this case because they are natural candidates for using as no certificates in recognition algorithms of hereditary properties. For example, if we consider a recognition algorithm for bipartite graphs, it is well known that we can adapt BFS in such a way that it recognizes bipartite graphs and also it returns bicoloring if the output is yes, so a bicoloring is a yes certificate, and it returns as no certificates odd cycles, which, as we previously said, are precisely the minimal obstructions of bipartite graphs. Well, now let's talk about some other definitions, which are exact neighborhoods and complete partitions. Well, imagine that you have a, a given graph and a given subset x of its vertex set. Okay, now for each subset of x, we are going to define the exact neighborhood of s with respect to x for sure as the set of all the vertices of the graph which are not in x, such that when we restrict their neighborhood to the set x, it is precisely S. Okay? And we are going to define the complete partition of the vertex set induced by X as the set P sub X, which contains as elements the set X and also all the exact neighborhoods of the subsets of X. Let's check an example. Okay, so here we have a set X of three vertices, the blue vertices A, B, and C, and we have that there are only 8 different subsets of X, which is the empty set, the set having only A, only B, only C, AB, BC, and AC, and finally the set having A, B, and C, which is precisely the set X. For each of them, we have the exact neighborhoods of these subsets, which are the vertices of the graph which are not adjacent to any of the vertices A, B, or C, the set of all the vertices adjacent to only A, the vertices adjacent to only B, vertices adjacent to only C, vertices adjacent to A and C, to A and B, to B and C, and vertices adjacent to A, B, and C. Okay, this is the complete partition. As you can see, this is in fact a partition of the vertices of the graph. Well, uh, okay, usually when x is small enough, we are going to avoid these brackets. So we are going to have this kind of notation, which is pretty clear, still pretty clear. Okay, one important thing about the complete partition is that whenever x is a fixed subset of the vertices of a graph G, then we can compute in linear time the complete partition associated to x using only linear space, and also for any two subsets of x, we can determine whether all the vertices in S are adjacent to all the vertices in T, or whether all the vertices in S are not adjacent to any vertex in T, also in linear time using only linear space. Well, this is important because we are talking about algorithms and we pretend to have efficient algorithms. Okay, well, finally, let's talk about matrix partitions. And well, a pattern is simply a symmetric matrix, let's say M, whose entries, all of them belong to the set having elements only 0, 1, and asterisk. Now, if we have a pattern of size n times n, let's say, an n partition of a graph is a partition, let's say b1 up to bn, of the vertex set of G, such that if mij equals 1, then that means that the part bi is complete to bj. That means that any vertex in bi is adjacent to all the vertices in bj. If mij equals 0, that means that no vertex in bi is adjacent to any vertex in bj. And if mij is an asterisk, then there is no restriction between the vertices, the adjacency of the vertices between bi and bj. So maybe some of them are adjacent, some of them are not, maybe all of them are or none of them are, we don't care about it. Particularly for the entrances in the diagonal of M, if MII equals 1, then that means that the set BI is a clique, and if MII equals 0, that means that the part BI is an independent set. Well, some important things about matrix partitions is that if you fix a pattern M, then it is easy to check that admitting an M partition is a hereditary property no matter the pattern you choose, and also that many important graph properties can be described by as the graphs admitting a fixed and a special matrix partition. For example, the class of bipartite graphs is precisely the class of graphs that admits a partition with this pattern. Here we have an independent set, another independent set, and there is no restriction between the adjacencies and on these two subsets of vertices. Also, we have, for example, the split graphs, a partition into an independent set and a clique and no restriction between them. And some other examples are, for example, the complete k-partite graphs. In this case is k equals 4, and the KL graphs or KL colorable graphs, which is a partition into k independent sets and L cliques and no restriction between different parts of the graph. Well, now we have all the necessary ingredients to talk about how to construct certifying recognition algorithms that uses minimal obstructions as no certificates, and that at the same time they use complete partitions as we defined it before. So in order to explain this, I am going to give you a very illustrative example that I developed together with Cesar Hernandez Cruz. And in this case, in this example, we are going to work with this pattern in tree that it has three parts, two independent sets and one clique. And we can see here that these two independent parts induce a bipartite graph because there is no restriction between these parts. And the clique is anti-complete to the bipartite graph. We can represent this with this diagram. Here we have the clique and we have the bipartite graph. This dotted line means that there is no restriction between these parts, and the absence of a line between these sets means that there is no adjacency between them. Okay, so this result says that a graph G admits an M partition, an A3 partition in this case, if and only if G doesn't have any of the minimal obstructions for this partition, which are the odd hole graphs, the 2K3, the diamond graph, and the pole graph. And also it says that there is a linear time certifying algorithms that serves as a recognizing algorithm, and which is also certifying, as we said, and it uses minimal obstructions as no certificates, and for sure A3 partitions as just certificates. So let's check how does this algorithm works. Well, it starts checking whether the graph is bipartite or not. Because if the graph is bipartite, we can simply consider the partition taking the bipartite parts uh, as parts B1 and B2 and just taking the empty set as the part B3 as the clique. And that's an A3 partition of this graph. So if the graph itself is bipartite, we are done. We have an A2 partition. If it is not, then it has an odd cycle, let's say C, with vertices 1, 2, 3, up to 2k plus 1, and returning to vertex 1. If this odd cycle C is long enough, if it has 5 or more vertices, then it is a not whole, and in that case we can return it as a no certificate, because in this case the graph is not a graph that can be partitioned with the pattern A3, since a not whole is a minimal obstruction for A3. Otherwise, if this cycle is not long enough, that means that this cycle has precisely 3 vertices. So we have a triangle, let's say with vertices 1, 2, and 3. In this point, we can consider its complete partition or the complete partition of the graph associated with the vertex set 1, 2, 3. Okay? And now we are going to check some things about the exact neighborhoods associated to this set. We start checking whether there is a vertex in some of the parts n1, n2, or n3. Because, for example, if there is a vertex in the part n1, then we take that vertex together with the 3 vertices of the triangle, and the graph induced by these 4 vertices is isomorphic to the pole graph. So in this case, we return this graph as a no certificate because the pole graph is a minimal obstruction for the pattern A3. Okay, and the same is true if there is a vertex in n2 or in n3. Okay, now we check whether there is a vertex in some of the parts n12, n13, or n23, because if there is a vertex here, then together with the 3 vertices of the original triangle, we obtain a graph isomorphic to the diamond graph, and again we return it as a no certificate. Well, now we proceed to check the behavior of the set n1 to 3, the exact neighborhood n1 to 3. And in this case, if we have 2 vertices in this set which are not adjacent, then by taking these 2 vertices and any 2 vertices of the original triangle, we obtain a graph which is isomorphic to the diamond graph, and we again have a no certificate for the property of having an A3 partition. So at this point, now we are going to check which is the relationship between vertices in n empty and the set n1 to 3. In this case, if there are vertices in n empty and in n1 to 3 which are adjacent, then by taking these 2 vertices and any 2 vertices of the triangle, we obtain a graph isomorphic to the pole graph, and we return it as a no certificate. Otherwise, at this point, we know that all the sets n1, n12, n2, n23, n3, and n13 are all of them empty. We know that n1 to 3 is a clique, so it is a clique also together with these 3 vertices because it is completely to all of them. And we know that n empty is anti-complete to the set n1 to 3 and also to the vertices 1, 2, and 3 because it's definition. So in this case, if n empty admits a bipartition xy, then we have this A3 partition of the graph, which is simply taking the bipartition of n empty to the sets b1 and b2, and the clique 1 to 3 together with the set n1 to 3 for the clique b3. Okay, so that happens if n empty has a bipartition. And now, what happens if n empty doesn't have a bipartition? Well, in that case, it has a knot cycle, again, C prime. If C prime is too long, then we return C prime as a knot hole. And in our case, it means that n empty has a triangle that together with the original triangle, it forms a copy of 2k3, so we return it as a no certificate. Well, This is basically what we pretend to do with this approach. And now I just want to tell you about some results that we already have and some ongoing work. Well, first, we know that all different patterns of size 3 times 3 that doesn't have asterisk, all of them admits this time of linear time certifying recognition algorithms using minimal obstructions as no certificates. This is a result of Cesar Hernandez Cruz with one of its students, Genaro Fernandez Velázquez, and also, a result of Cesar and me is that also for all pairs of size 3 times 3 having 1 1 except one pattern, all of them admits also this kind of certifying recognition algorithms in linear time. Well, in an ongoing work joined with Germán Benítez Bobadilla, Juan Carlos García Altamirano, and César Hernández Cruz, we are working on a similar results now in this pattern of time of size 3 times 3 with two asterisks out the main diagonal, and also in a ongoing work, but this time with my postdoc advisor Juan José Montellano Ballesteros, we are working on similar results for the class of graphs that admit a partition into an independent set and a set inducing a complete multipartite graph, which are called counipolar graphs, and which in fact generalize this partition in the sense that this partition is a partition into an independent set and a complete bipartite graph. Okay, so this is what I was wanting to tell you today. So thank you for watching this video and see you next time. Bye bye.